Now what we're going to do is we're going to look at series and parallel circuits, but we're going to say, hey, what happens if I have capacitors in here? Remind you of the capacitor equation. Q is equal to charge is equal to capacitance multiplied by voltage. Now let's just start off with capacitors in parallel for a second here. Now if you remember, for resistors in series, kind of look at this contact of the positive terminal. It's going to put the same amount of potential across each one of these three capacitors. So the voltage across this one is going to be the same as the voltage across that one, is going to be the same as the voltage across that one. Now suppose I knew what these three capacitances were, I can figure out what Q1, Q2, and Q3 is simply by saying Q1 just like that, Q2, C2, V, and then the same thing for Q3. It turns out that I could say, hey, I can reduce this circuit into some equivalent capacitance, much like I did with resistors, and I know that I'm going to have some voltage across this guy, and I could say, hey, if I can reduce this to some equivalent capacitance, then I could say, QEQ, or Q total, is going to be equal to CEQ multiplied by the potential. How do I do that? Well, here's the kind of the equation I had just finished writing. We know that charge is going to be a conserved quantity. So the total charge in the circuit must be equal to charge 1 plus charge 2 plus charge 3. So I can say that charge 1 is C1V, same here and here. Pull out the constant V, and we're left with the equivalent capacitance to be C1 plus C2 plus C3. Now this is going to be the case of capacitors in parallel. Note that it looks very, very, very similar to resistors in series, so you have to be very careful. Are you dealing with capacitors or are you dealing with resistors? The reason why we have to be extra careful is because if we look at capacitors in series, it turns out that it's going to look like resistors in parallel. Kind of picture this setup right here where we have three capacitors that are in series. Turns out the capacitors in series are going to have the same amount of charge on them. So this potential is going to put some positive charge here, some negative charge here. You can kind of picturing that pulling the charge from over here, so this positive charge must be equal to that negative charge, kind of so on and so forth. So that says that I could write, use this equation right here to say V is going to be equal to Q divided by C1, V2 is going to be equal to Q divided by C2, and the same for this guy right here. Now, much like resistors in series, potential must be, or resistors in parallel, potential must be conserved. So if you kind of think about it, V1 plus V2 plus V3 must be equal to this voltage right there. So this is just kind of all that in writing. Add the voltages up. Remember that V is going to be equal to Q divided by C. So I could essentially take my diagram from the last slide and say I can write that as some circuit with some equivalent capacitance, CEQ, and then my potential. How can I get this equivalent capacitance? Well, essentially I'm going to take, say, my voltages are going to be conserved, so I can write my equivalent circuit to be the sum of those three. Pull out the common guy, which is going to be charge, and then we could say, hey, look, equivalent capacitance is going to be 1 over C1 plus 1 over C2 plus 1 over C3. Again, much like with a resistor, make sure that you flip the equivalent capacitance over at the end of the day. Now let's take a quick look at RC circuits, resistor capacitor circuits, and for the sake of sanity, we're only going to look at these guys in series. So kind of taking a look at my circuit down here, here I have a battery, here I have a resistor, and here I have a capacitor and a switch that is initially closed. So what would happen if I say close that switch? Well, logic would say, well, you have a break in these wires right here in the capacitor, and so current shouldn't flow, but it turns out that current is actually going to flow. You can kind of imagine these negative charges flowing to this side of the capacitor and building up some negative charge, and kind of similarly, negative charges are going to run to the positive battery over here and build up a net positive charge on this side of the capacitor. Now, this buildup of charge is not going to happen instantaneously, so this charge is actually going to be a function of time. And of course, remember, Q is equal to capacitance multiplied by voltage. If charge is a function of time, so also must be voltage. if I were to plot the voltage of this capacitor as a function of time, you kind of see a buildup with this neat little funky curve like here, right there. And at the end of the day, the voltage of the capacitor is simply going to be equal to the potential from this EMF source, the potential of the battery, if you will. And you can kind of see that we have, initially it's going to have 0 voltage. At some time later, the time being equal to the resistance multiplied by the capacitance, we're going to have 63% of the voltage. And then at 2RC and 3RC, by about 3RC, it's probably got about 99% of the EMF on it. How much current is flowing? Well, initially a whole lot of current flows, but as the capacitor builds up more and more and more charge, less current is going to flow. And then kind of at the end of the day, there's going to be essentially no current flowing through the circuit, because as I mentioned, it is indeed broken. We can kind of see that this resistance multiplied by the capacitance is going to be kind of an important thing to talk about when we talk about RC circuits. Now, the funny shape of that curve in the last slide actually comes because if we were to write the potential as a function of time, it turns out to be an exponential fit. So here we could say this is going to be the voltage of the capacitor. That's kind of the EMF of the battery, the potential of the battery. And we can see that the time behavior is going to have this exponential in there, where it's going to be e to the negative time. So that's going to be time divided by this resistance multiplied by the capacitance. We can see that if time is going to be equal to 0, we evaluate this guy, and evaluation of e to the 0 is going to be 1, and so we have 1 minus 1. Potential is going to be equal to 0 at time is equal to 0. And kind of similarly, if we said, hey, what happens when time is equal to infinity? Well, in that case, e to the negative infinity is going to be 0, and so at t is equal to infinity, the voltage is going to be equal to 0. And you can kind of see that the potential at any given time is going to depend largely on the resistance multiplied by the capacitance. So suppose I knew the resistance and the capacitance, and I said, hey, what is the potential at any given time? Hey, that's pretty simple. I can evaluate that. Since Q is equal to, or since charge is equal to capacitance times voltage, the charge is going to have a very similarly looking curve, so we can kind of write it like that, where the charge at any given time is going to be equal to the initial charge that's on that guy, and then 1 minus e to the negative time divided by RC. Again, this resistance multiplied by the capacitance is going to dictate how fast the potential changes, how fast the charge builds up. So it's actually called the characteristic time constant of an RC circuit. Now the nice thing about RC circuits is if I wanted to look at just a capacitor and resistor hooked together, where the capacitor initially has got some charge on it, so it's got some initial charge and some voltage, and I were to say, once again, throw this switch, I could say, hey, what is the charge and voltage going to look like? Well, it's going to decay over time as the resistor slowly eats away at my voltage. And what we can do is we can say that the charge is going to just exponentially decay. So my charge is going to be equal to my initial charge multiplied by e to the negative time divided by this time constant right there. And if I were to look at my voltage, initially it's going to be very large, but as the resistor kind of chips away at it, it's going to exponentially decay over time. And you can kind of see the time constant is also going to be kind of important. At the time being equal to the resistance times capacitance, I'm going to have 37% of my voltage, and when I'm at 3RC, I'm going to have 0.01% of my initial voltage. So this one's actually a little bit easier. You don't have that 1 minus in the equation to worry about. Now the last thing of this chapter is how do we actually go ahead and measure current and measure voltage. So let's introduce ammeters and voltmeters. Essentially, an ammeter is going to measure current and a voltmeter is going to measure voltage. Let's just talk about ammeters here for a second. Essentially what you want to do is you want to put ammeters in series. So ammeters must always be in series to measure the current, but you want to make sure that it has a very low resistance, because you don't want it to affect the current in a circuit. So kind of taking a look at this circuit right here, I have some ammeter. It's hooked in series with these two resistors that are in parallel. So I'm essentially going to be able to measure the current right here. I'm going to have some current flowing here, some current flowing here, so I could have I1 and I2. And these hook more ammeters in series, and I could actually measure I1 and I2. And you'd expect from Kirchhoff's junction rule that I1 is, the current is going to be equal to I1 plus I2. Now suppose I said, hey, what happens if I just hook an ammeter up in series? So taking a look at this circuit right over here, where I just have current flowing through a resistor. Remember that ammeters are going to have very low resistance. Current is going to take the path of least resistance. So this current right here is going to preferentially take this path, very low resistance ammeter, and essentially burn it out. So you never want to hook an ammeter up in parallel. Now, voltmeters are actually going to be the exact opposite. You don't want the voltmeter to affect the voltage across the circuit element. So you're going to hook it up in parallel, and you don't want current to flow through it, and so the resistance must be very large. So here I want to measure the potential from A to B. I hook a voltmeter across it. I don't want the current to take that path right there, so I'm going to say that the resistance is actually going to be approaching infinity. What this also means is, hey, suppose you said, what happens if I accidentally hook a voltmeter up in series? So here I say I'm just going to attach some wire right here, and initially I had some current that was flowing through this resistor right there. Well, since this resistance is very large, infinitely large, so R is going to be large, current's not going to flow through this resistor right here, because the voltmeter is essentially taking all that potential and eating it up. And I'll just kind of finish off with just kind of paging through the summary slides here.